In this presentation, I will be explaining how oxygen binds to heme within hemoglobin, the structural changes that occur during oxygen binding, and how oxygen binding capacity differs between the lungs and systemic capillaries. I will also explain how carbon dioxide interacts with water to influence blood pH in the capillaries, which ultimately affects oxygen release. Understanding this process is critical because hemoglobin allows oxygen to be transported efficiently from the lungs to tissues throughout our body. So, what is hemoglobin? Hemoglobin is a globular protein found inside our red blood cells, or also known as erythrocytes. It is composed of four polypeptide subunits, two alpha subunits, and two beta subunits. Each of these subunits contains the prosthetic group, also known as a heme. The heme group is composed of a planar porphyrin ring structure that coordinates a central iron ion in the ferrous state, which is Fe2 plus. The iron atom is coordinated to four nitrogen atoms in the porphyrin ring and also interacts with a proximal histidine residue from the globin protein. Oxygen binds reversibly to the iron atom in the heme group. Because hemoglobin contains four heme groups, one hemoglobin molecule can bind up to four oxygen molecules. This reversible binding allows hemoglobin to load oxygen in the lungs and then release it in our peripheral tissues. When oxygen binds to the iron atom in heme, it induces a structural change in hemoglobin. In the deoxygenated state, hemoglobin exists primarily in what is known as the T state, or also known as the 10th state. In this conformation, the iron atom sits slightly outside the plane of the porphyrin ring. When oxygen binds to the iron is pulled into the plane of the porphyrin ring. This movement also pulls the proximal histidine residue attached to the globin protein, which results in a conformational change in the entire hemoglobin structure. This conformational shift converts hemoglobin from the tense state into the R state, or as we call it as well, the relaxed state, which has a higher affinity for oxygen. This process demonstrates cooperative binding, meaning that once one oxygen molecule binds, the affinity of the remaining heme groups for oxygen ultimately increases. Okay, so now that we've gone over structural changes during oxygen binding, let's see how oxygen binds in the lungs. Oxygen loading occurs in the lungs, specifically within the alveoli, which is where gas exchange takes place. In this environment, the partial pressure of oxygen is high. This high oxygen concentration promotes oxygen binding to hemoglobin. Under these conditions, hemoglobin shifts towards the relaxed state, which increases its affinity for oxygen. As oxygen molecules bind cooperatively to the four heme groups, hemoglobin becomes highly saturated with oxygen. At the oxygen partial pressures found in the lungs, hemoglobin can reach approximately 97 to 98% saturation. So, now we're going to talk about how oxygen releases into our systemic capillaries. Once oxygenated blood travels to systemic tissues, the environment actually changes quite significantly. In actively metabolizing tissues, oxygen is constantly being consumed for cellular respiration. As a result, the local partial pressure of oxygen is much lower than it is in the lungs. Because of this lower oxygen concentration, oxygen begins to dissociate from the iron in the heme groups. As oxygen molecules leave hemoglobin, the protein gradually shifts back towards that 10th state, which has a lower affinity for oxygen. This allows oxygen to then diffuse from hemoglobin into surrounding tissues. We also can't forget how carbon dioxide reacts with water. In addition to transporting oxygen, blood must also transport carbon dioxide produced by cellular metabolism. Within our systemic capillaries, carbon dioxide diffuses into red blood cells. Inside those red blood cells, carbon dioxide reacts with water in a reaction catalyzed by the enzyme carbonic anhydrase. The reaction forms carbonic acid, represented chemically at the top of this presentation slide. Carbonic acid rapidly then dissociates into hydrogen ions and bicarbonate ions. Lastly, let's look at the effect of pH on oxygen release. This is known as the Bohr effect. The increase in hydrogen ion concentration from carbonic acid formation actually lowers the pH of blood in our systemic capillaries. This decrease in pH affects hemoglobin's affinity for oxygen. Lower pH actually stabilizes the T state of hemoglobin, which reduces its affinity for oxygen. As a result, oxygen is released more readily from hemoglobin in the tissues, where carbon dioxide production and acidity are higher. This phenomenon, like I stated in the beginning, is known as the Bohr effect. Okay, so in summary, hemoglobin transports oxygen through reversible binding to iron within heme groups. Oxygen binding causes a conformational change that shifts hemoglobin from the tense state to the relaxed state, increasing oxygen affinity. In the lungs, high oxygen levels promote oxygen binding, allowing for hemoglobin to become nearly fully saturated. In our systemic capillaries, oxygen levels are lower and tissues are actively consuming that oxygen, which promotes oxygen release. At the same time, carbon dioxide produced by tissues reacts with water to form carbonic acid, generating hydrogen ions and lowering pH. This decrease in pH further promotes oxygen release through the Bohr effect. And together, these mechanisms ensure efficient oxygen delivery to our tissues and removal of carbon dioxide from our body.